Hello, my name is Brian Moreno.
I'm Sean McKenrick.
We're going to be talking about nanofluids and their effect on heat pipes. So the problem that we have with PCs is that they're microprocessing units, also known as MPUs. They tend to generate a large amount of heat. For example, certain units from 1995 through 2002, they generated up to 30 watts of heat. And it's been predicted that future generations of MPUs they're going to exceed 300 watts of total power. So what people have been using is heat pipes to try to combat this heat, to try to create a substantial amount of a cooling effect on the MPUs. So the article that we actually looked at, they studied the thermal performance of screen mesh Wick heat pipes when using different nanofluids as a working fluid. They also took a look at the effects of the nanofluid concentration on the heat pipe performance, and also how the nanofluid affected the structure of the screen mesh wick. Next slide. So essentially what nanofluids are is just, they consist of nanometer-sized particles known as nanoparticles, and they're combined with the base fluid. The nanoparticles tend to be either of metals, oxides, or carbides, while the base fluid is usually water, ethylene glycol, or oil. And one thing to mention is that the article that we looked at, they said that previous research has shown that the effective thermal conductivity of nanofluids tends to increase with increasing temperature. And also that by increasing the nanoparticle concentration in the nanofluid, increases the performance of the heat pipe. Next slide. So to perform the experiment, what the researchers did was they began by preparing the nanofluids. Here on the table, what we see is the different nanoparticles that they used. They either used aluminum oxide, titanium oxide, or zinc oxide, and they combined that with the base fluid either of distilled water or ethylene glycol. So what they first did was combine the nanoparticles with the base fluid by a process known as ultrasonication. After that, they placed the nanofluids into a thermostatic circulating bath, which was kept at a constant temperature of 25 degrees Celsius. And from there, they measured the thermal conductivity, but they recorded it as a ratio of the thermal conductivity of the nanofluid to that of the base fluid. And then finally, they determined the concentration of each of the nanofluids, which it ranged from 1 to 5% with increments of 1. And then here in the figure at the bottom left, what we see is the relationship between the concentration and the thermal conductivity of each of the nanofluids. So the blue, the black, and the red lines, this is data collected from this experiment that mentioned in the article. And the green line is actually from data from another article from previous experiments. But overall, what we see is that as we increase the concentration of the nanoparticles, the thermal conductivity increases as well. And then just based on these fluids that are seen in the figure, the aluminum oxide, ethylene glycol nanofluid had the largest thermal conductivity. Next slide. And so for the experiment, the heat pipe consisted of a copper tube with an 8mm outer diameter, 7.44 millimeter inner diameter, and a total length of 200 millimeters. And that was paired with a screen mesh wick made of stainless steel with a wire diameter of 56.6 micrometers and about 67,000 plates per millimeter. And it consisted of 4 layers of this screen mesh. Next slide. And then here we just see the overall experimental setup that the researchers used. Just some things that we would like to emphasize are the heat pipe itself, which is labeled by the circled 4. We can see the different sections of the heat pipe, the condenser section, adiabatic section, and the evaporator section. And then also throughout the heat pipe, we see these black dots. These just indicate where the researchers took their temperature measurements using K-type thermocouples. And then by the evaporator section, we can see that it's wrapped around this component labeled 5, which is actually a heater that was used to regulate the temperature at the evaporator section. And then all the way to the left, we see the circulating bath labeled by the circled 1. This was used to control the temperature of the condenser section and keep it at 25 degrees Celsius. Next slide.
All right, for the results of this experiment, we can start here with figure 7. What this shows is a temperature distribution profile and screen mesh wick heat pipes and commercial sintered wick heat pipes, where water and nanofluids of aluminum oxide water are used as working fluids, and a 30-watt heat load was applied during the experiment. This shows the temperature difference in the heat pipe tends to decrease with increasing volume concentration of nanofluids. This indicates that the concentration of the aluminum oxide water nanofluid has a significant effect in reducing the temperature of the evaporator. Next, here in figure 8, we could see a plot of the thermal resistance of the heat pipe versus the heat load. Here, the heat load is varying and can be determined from the equation Q equals VI, where V is the input voltage and I is the current. We're assuming that there's no heat loss due to perfect insulation. And here, the thermal resistance is determined by the equation R equals TE minus TA over Q, where TE is the evaporator temperature and TA is the adiabatic temperature. From this plot, we can see that the thermal resistance of the heat pipe decreases with increasing heat load. And additionally, we can see that the heat pipe with a 5% concentration of aluminum oxide has a better performance than with water alone as a working fluid. Next, here in figure 9, we have a temperature distribution plot versus the distance from the evaporator for all of the nanofluids with the same heat load. What we can see here is that the heat dissipation improves for all of the nanofluids when compared to their respective base fluids. And from this plot, we can also see that the lowest temperature at the evaporator for the same heat load was observed with aluminum oxide water. Next, here in figure 10, we have another temperature distribution plot versus the distance from the evaporator with a varying diameter. And this shows that increasing diameter of the heat pipe increases the diameter of the convective heat transfer, mass flow rate, and absorbed heat. And on this plot, we can see that by increasing the diameter, you increase the performance of the heat pipe. Next, here in figure 11, we have a plot of the heat transfer coefficient of the evaporator versus the heat flux of the evaporator for aluminum oxide water with a varying concentration. Here, HE is the heat transfer coefficient of the evaporator section, QE is the heat flux of the evaporator section, and HE is determined from the equation HE equals QE over delta T, where delta T is the difference between the average inner wall temperature and the steam saturation temperature. QE is determined from the equation QE equals big Q over 2 pi R naught LE, where LE is the length of the evaporator, R naught is the outside radius of the evaporator, and Q is the heat load. From this plot, we can see that aluminum oxide water with a 5% volume concentration has the highest heat transfer coefficient. Next, here in figure 12, we have another plot of the heat transfer coefficient of the evaporator versus the heat flux for all of the nanofluids. These curves show that the increase of the heat transfer coefficients compared to the heat transfer coefficients of their respective base fluids, and it can be seen that these curves are similar to the increase in the thermal conductivities of the nanofluids that were discussed previously. This indicates that the increase in the effective thermal conductivity of the working fluid correlates to the heat transfer coefficient. Next, here we have the effects of the coatings from the use of the nanofluids on the screen mesh. And these effects from the nanofluids on the screen mesh were found to improve the capillary structure of the wick and improve the surface wettability by increasing the surface roughness, as well as increasing heat flux. And to wrap this all up, from this experiment, the screen mesh heat pipe with the aluminum oxide water nanofluid with 5% concentration had the best performance. Additionally, the coatings on the screen mesh resulted in good capillary structure. And lastly, this experiment proves that the use of nanofluids and heat pipes can result in higher thermal performances, which makes them an attractive substitute for conventional working fluids.